So, welcome to today's seminar. Thank you for coming here to this a bit more remote room. I'm happy to welcome Alexandra Carvalho today, who is at the moment at Peking University and will speak about Higgs boson pair production. She did her PhD in Sao Paulo in 2014 until 2014, and then was a postdoc in Padua, in Tallinn, and in Vilnius. She has been a subgroup convener of the extended Higgs subgroup, and there's a number of contact and coordination role. One is the Monte Carlo and interpretation coordinator for the standard model studies, and another one which I would like to mention is now the contact for Higgs projection studies. So the floor is yours. We look forward to your seminar.
Thank you. Is it the mic? Is it okay outside?
We can hear you.
Okay. So let's start. It's a pleasure to be here to talk about the CMS searches for Higgs boson pair production with a very new result that we have. Starting with a bit of motivation, as this is a seminar. We have the standard model of particle physics that is a very nice description of our non-matter and 3 of the 4 elementary forces of nature: strong force, electromagnetic, and the weak force. The Higgs mechanism is the simplest way to unify 2 of those, that is the electric interactions, with a very simple doublet that comes with postulated, almost God-given, as simplest as possible potential that contains 1 mass term and 1 self-coupling. Then, given this potential, because of spontaneous symmetry breaking of the electric vacua, we'll have the mass of the weak bosons, that is very well measured, plus a scalar particle, that's the Higgs boson. Once his mass is null, how many things are predicted in nature, like the mass of unknown particles and the shape of once the shape of the Higgs potential is determined by the Higgs self-coupling, we also know the fate of the vacuum expectation value of the universe, that by now, given the Higgs mass, we are borderline metastable universe. The trick here is that any deviation of the Higgs potential disbalance all the predictions, and then this is a clear sign of new physics.
Or I give you the one to hold.
Like this? Okay, one to hold.
This one?
I'm a bit sick, so my voice goes a bit low. So the Higgs boson was finally discovered by the Atlas in CMS in the 2 experiments at the LHC in 2012. And since then, we have many studies that measure the Higgs boson properties. For example, the Higgs boson mass, here I show an Atlas result, is measured with very much precision, with a lot of precision, 0.11 plus 0.09 GeV. And the particle masses relations with the couplings that comes from the Higgs potential are also very much following what is the standard model would predict for vector bosons for the 3rd generation of fermions, and starting to get measured for the 2nd generation of fermions. Other properties that are also well measured are the width. We have a very small room for invisible width of the Higgs, and the spin parity properties. So what is missing in all these big pictures is the Higgs potential. So a measure of the Higgs potential is a closure of the standard model, or a dot to understand the physics behind it. It's like you have a puzzle that is mostly done, and a cornerstone piece that when you try to put, if it fits, you have a full picture of the theory. If it not, it means that you are missing a whole lot of pieces to mount this puzzle. So the search for the measure of this lambda of the self-coupling is measured at the LHC with the directly to the production of Higgs boson pairs. Here is one figure of what would be the cross-section of Higgs boson pairs. It's quite old, but gives the picture of that the main production mechanism are Gluon-Gluon fusion. I'm going to go into it, in vector boson fusion. From now on, when I talk about couplings, I always talk about deviations from the standard model. This means using kappa framework. So instead of lambda, I use kappa lambda or kappa top. So we start with Gluon fusion production. It's in the standard model that's predicted as a mixture of a loop-induced process that have very destructive interference. In here, you can see, for example, a picture of what would be the cross-section in terms of the mass of the Higgses, of the two Higgses, of this diagram that you call box, this diagram that we call triangle, and interference. You see that they have negative different signs and end up in a very specific shape for this model with a small cross-section doing this destructive interference. When you start to have deviations from kappa lambda, you start to have a softer signal, but with much higher cross-section, as we had seen in the last slide. Because Higgs boson production is a loop-induced process, is a bit challenging from the theory side already to simulate it and to measure its cross-sections. In the simulation itself, the first searches that we had, this was modeled using form factors to model the loop of tops. It was the best we can have in 2014, 2016, new simulation scheme in a power generator called PowerEgg was done with a full model on QCD next to the other predictions. So jets and gluons and quarks coming up of the loop. The next things that came was the BSM-like processing math. I'm going to come into it in a bit. But also total cross-section have evolved considerably. Total cross-section is something that you can calculate with a bit more precision. So you see here one picture that I stole from Michael Spira in a workshop here at CERN a couple of weeks ago, that the first measure, the first calculation of the Higgs boson was around 20 femtobarns, but with a huge cross-section due to the top loop. And since then, it's evolving. This is also converging in how much evolves by time. We had, for example, an update in 2021. That is what we use here. That got slightly updated since the last combination because of Neraton. But since then, there is already a new state of the art. That is the three next to the other with heavy top approximation. These people still need to work because we still have large uncertainties. And this is because of the top mass in the loop still. Then come for the second process that I'm going to describe in detail. That is a vector boson fusion. That's a 3-level process that happens when two quarks irradiate a vector boson, and this vector boson irradiates by itself, or a Higgs boson pair. The cross-section for this process is much slower because it depends on quark initiated process. So it's kind of 1.7 femtobarn at 13 TeV. But one thing interesting in this process is that we can probe the VV-HH contact interaction. That's a direct test of doublet structure of the Higgs field. That is also quite important to determine how the potential is done. Yeah. Here you have a figure of it's always the same problem. Once you parameter, you have interferences between the diagrams, and when you arrive to the distributions, they are heavily dependent on the value of the couplings. Any deviation from the standard model or the total gets a harder signal. So if there is, but this is if we postulate that there is only the standard model processes are there. But if you have new symmetries or new super heavy particles that can be integrated out and generate more contact interactions with gluons and tops, especially in the for the gluon fission production, you can have BSM-like couplings, and those provoke much more violent variations of the cross sections and topologies. So we assumed variations of those in the Higgs CFT. We call it heft. That are linear variations of the couplings. I must mention, though, that other things can happen, alternative approaches. An alternative approach to this linear variation of couplings is the standard model EFT, called SMEFT. In this one, the symmetries that are existent with the standard model, the IC2 symmetry, it's assumed to govern the standard model Lagrangian and introduce correlations between all those couplings, among other data within the simulation. Other thing that can happen also as new physics in Higgs bar, it's the presence of resonances. This is something I'm not covering at all here, but I point to you a review that we did in CMS, especially if these new particles have new additional Higgs bosons in the Higgs potential. All the couplings of the 125 particle we find are slightly changed. So this is also can happen. Anyhow, yes, from heft. It's the tool that came first. So we assume we do this in both ways. We have upper limits in the representative signal topologies that we call it shape benchmarks. Here I show how more violent the variations can come. I'm showing one of the shape benchmarks that is more threshold-like. So we have all the events here very much clustered in the low energy, and also the one that is most boosted, that is when you have harder events. We also do parameter scans. In this, we give priority to this contact interaction TT-HH that we call it C2, because this is deeply connected with kappa lambda and kappa T in most complete theories, like for example, this math I mentioned, or the standard etc. So this I told about the theory saga in computing production of Higgs boson, but we also have the experimental saga, and now more special for this experiment, for this seminar, the CMS one. Since the Higgs discovery in 2012, we had the first non-resonant Higgs search. Most of us seeing what we could see at this at the Run 1 environment, and we arrived with the tools at the moment at something around 1720 times the in the kappa lambda deviations of kappa lambda. Since then, we have very much a lot of results with full run 2 data, and now the theory updates. And then with these, we had a combination of full run 2 HH searches that was published in Nature in 2022. From this, we added more channels and did a combination with single Higgs, but also we added more channels and theory updates, and arrived to the main result of the seminar, that is the legacy combination of random searches that we kind of arrived to a kappa lambda, I anticipate, between minus 1.4 to 6.4 at the full run 2 data. So this talk, I cover the legacy and talk a little bit of the measurements, the combined measurements with the single Higgs. How to look for Higgs boson CMS? We can identify very much very good objects, photons, electrons, and muons as a clean signature. They don't appear that often in a background, but also we can identify more hadronic objects that are jets, tagged or not as a B, and hadronic tall leptons that if you see here how the Higgs boson decay, they hold a big portion of the Higgs branching ratio. Then we'll have the case to photons, taus, and B jets, the case in which we lose not much energy when reconstructing objects in the detector. Anything that comes from leptonic decays from W or tau leptons that are not hadronic involve a neutrino, and then it's imperative to have a multivariate of analysis to recover this loss of energy. So when you talk about channels, we have again balance between resolution, reconstructability, and a branching ratio to define its importance. So what we have as a CMS, we have rich coverage of Higgs bar. Here you see the table of final states. In the numbers, you have the branching ratios, and we cover everything that have a reasonable branching ratio that is not a pair of gluons. That is something that we cannot tag, for example, that we have less control in the background in tagging it. Here is the list of publications that we have to cover in this table. You see that it's a lot of work. It comes from 2021, the first, and it's a lot of work and there's a lot of time. One thing that in this previous, in this analysis that are more ancient with respect to the new, we, for the legacy combination, included the heft and the shape benchmarks, especially to this publication. So what I'm going to cover to have an idea of how we talk, how we extract the information about Higgs bars. It's the main 4 channels that you're going to see in the upper limit, and the newcomers, everything that these 3 new channels that are coming with this new pass. First, we have the 4B final state that have the largest branching fraction, but also a large KCD background. And here you have 2 kind of regimes to cover. One is in which each Higgs boson decays to resolve at B jets. So we see 4 jets in the detector, and you identify this event using the B jet identification in each of the jets. Then you use some pairing to understand which pair is most likely to come from each of the Higgses. And in these paired jets, we define control regions in which we can predict a data-driven prediction of the background. When with this prediction, we do a multivariative analysis to extract the signal. In gluon fusion, as in vector boson fusion, you have much less background, or you can do a fit in the mass of the Higgs bosons. Then we arrive to the fully boosted scenario, where you have this each one of the Higgs bosons. It's very, very energetic, and therefore the case to the two B's that comes from the decay, they appear collimated large cone jets. And for this, we had identification of those jets based in a graph neural network that brings considerable background reduction, making that we can even use Monte Carlo templates to estimate the background. So these, and then also to not rely that much in multivariative analysis, only for signal background separation, but in the fit itself, you can already see mass peaks in for the DGF, they fit the Higgs mass, for VBF, the Higgs mass again. You see that they have a good sensitivity to the standard model, and the boosted case, because I said that when you vary kappa to V, this is especially good constraining the anomalous kappa to V. We combine both searches for the combinations and remove the overlap, always giving priority to the boosted. That is cleaner. Then you have the other two of what we call golden channels, that is BB gamma gamma and BB tau tau. They have somehow a smaller background, but a better background control, especially in BB gamma gamma, where I have MVA to separate the main backgrounds. But then when you do that, you can look for, in the data-driven estimation way, for a peak in the Higgs mass in a smoothly fired background in the M gamma gamma, and here into the also in the in the mass of the two B's. One thing to pay attention here is that as we have a very good peak resolution when looking for M gamma gamma, also events that come from single Higgs production, especially TT, the associated production of top quarks, are important on constraining what is coming from single Higgs production, what is coming from Higgs production. So have a separate area to constrain that in the fit. You have to observe the times the standard model. Last of the golden ones is BB tau tau. BB tau tau, we had a deep neural network that's called internally deep tau that was developed exclusively for this analysis. And this brings considerable, again, background reduction, because more you can identify objects out of the hadronic side, more you reduce background, then you can look for Higgs bar, what they do in a multivariative analysis. This analysis, one nice thing for me is that consider events with merged HBB jets as well. So it's a good, also good probe of kappa to V. Then the newcomers, that the BBVV hadronic, and here we are going to more and more energetic objects. In some sense, you have a Higgs that come to a collimated jet, as we discussed before, but another Higgs that comes to a collimated pair of vector bosons that ends up in a 4 courgette. And therefore, for this final state, with a large branching ratio, it was developed an identification for this identification tagger for this 4-jet object that again helps with background. And after NVAs and use of the tiger, you can arrive to 69 times the standard model. However, as a first attempt of this vector boson to 4-jet courgette collimated jet, it's a very nice thing. And because of this is in the boosted side, again, this is very good for kappa 2V, and we are going to see it after. Then you have other 2 newcomers for this new combination, that is WW gamma gamma and tau tau gamma gamma. Then we completely close the possibilities of a double Higgs decays in that table I showed before. And here, the things look very much like the BB gamma gamma search, with the difference that we don't have the BB anymore. So we have NVA to separate the backgrounds, but when you want to extract signal, again, you do a data-driven estimate of how a peak would look like in a strictly falling background. It's interesting to see that, especially in the tau tau gamma gamma that have 0.003% of branch inversion, very tiny, we arrive to 30 times the standard model. It's remarkable. So results of the combination, everything that we have more complex, most complete and most up-to-date for the run 2, we set limits in 3.5 times the standard model observed, and the best genus, the 4B, BB, tau tau, BB, gamma gamma, but you also see a complementarity with the other channels. For example, the difference from the combination to the 4Bs itself, it's almost a factor 2. So it was worth to go to the job of doing all the channels. We also set upper limits considering coupling scans, and the couplings that new and that we can measure only in the double Higgs production, when the other couplings are set to the standard model value, here kappa lambda and kappa 2V. And we also set coupling constraints in 2-dimension. Here, for example, you see a 2-dimensional constraint of kappa lambda over kappa t. You see a slight correlation on the measurement, but not much. Also, the observed is not that far from the expected. It's everything within 1 sigma. Here, when considering the kappa 2V coupling, the constraints are dominated by the VBF channel, but everything is considered in the loop, such when you do 2-dimensional distributions, you see that kappa 2V, kappa lambda, kappa 2V CV, you see here in this line is for 5 sigma exclusion. You see that kappa 2V equals 0. It's excluded more than 5 sigma to any value of kappa lambda and kappa 2V. It is a very strong assumption that the coupling exists. Then we have the results in the BSN-like scenario, as I said in heft. For this, we have the C2 scan. We constrain here C2 by upper limits between 0.3 and 0.63. at 95% confidence level, and that can be translated when you have more complete theories and what is the reach of new physics. One interesting thing is when looking to the best fit, here in orange, you see the expected at 0. It's a BSM-like coupling, but the fit prefers 0.5. It's still statistically compatible with the standard model, but it's interesting to notice. Again, on Chinese complementarity, when you look at couplings, you see that in kappa lambda here, the difference between the combination and the most constraining channel, it's considerable. So the combination is worth it. Also in T2, in kappa 2V, you have a domination of the constraint by the boosted 4B channel. So that's what happens. The last results in the BSM scenario are the shape benchmarks. And here you have two sets that you consider. One that is agnostic to the kappa's constraints. One is that considering the kappa constraint when doing these scans for anomalous shapes. And you see that in the part of that is agnostic, even if you have more than 1 order of magnitude of difference in the upper limit coming by these violent shape variations, still everything is compatible with the standard model. We also have here supplementary, the breakdown of these upper limits by channel. And then we can see how the complementary of channels change if the topology of the channel change. Two things are when you have softer MHH, BB gamma gamma and BB tau dominate the limits. When you have harder, then it's will be boosted. But we want to measure kappa lambda. And as I mentioned before, the measurements of kappa lambda and kappa 2V are very much entangled with couplings that are better measuring single Higgs production. For example, kappa top, the coupling of the Higgs with the top, and the kappa V. That's not the whole story, though. I think I oversimplify it. It happens that at one loop in the electroweak, the single production here in associated with vector bosons or in gluon fusion, vector boson fusion, or associated with tops, they depend on kappa lambda, and these can be computed. For example, in 2017, we had these first computations. It was not the first. The first considering the changes of our signal topologies. And therefore, when you are considering the measuring kappa lambda, the ultimate precision that we can have in kappa lambda and therefore in the Higgs potential in the standard model scenario, because when you do these calculations at one loop, you very much rely on the standard model scenario, you need to consider a single Higgs process. And one interesting thing is that in single Higgs processes, if they are done in such a granular way, being in energy and reconstructed areas, that is something called the simplified triplet cross-section, you can also take into account changes in the signal topology, not only production rates. All of these effects are considered in the Higgs combination, but I didn't want to bother you there with that. But here for the Higgs plus Higgs combination, they are very much important. The result, as I said, was made prior to the legacy combination I just showed. So we have mostly the main channels for Higgs per production, as shown before. And you have a whole lot of channels considering a plethora of Higgs boson decays produced in gluon fusion, PBF, associated production with atom bosons, and associated production with tops. So we cover everything. Some of the searches have this simplified empirical section. We also cover at differential level. So this is what happens with the combination. In a combined measure, we are able to achieve better precision in kappa lambda, and also we are able to have this precision in kappa lambda and the minimal assumption of the other Higgs couplings. For example, we can float them in the filter and then see what would be our precision in kappa lambda. And here you see how one-dimensional in the standard model scenario for the other couplings look like in the combination between single Higgs in blue, double Higgs in orange, and then you have this red here. That is the most precise measurement given this data set. Here you have kappa d kappa lambda. You see that we had a very large uncertainty in kappa t when you put single Higgs on it. You very much constrain what can be the value of kappa t of kappa lambda given any value of kappa t. And here for kappa 2v and kappa v, you also have everything very much compatible with the standard model. What is boring, but is remarkable. So we have all those results, but we still don't see Higgs pairs. When do we expect to measure them? So it is an estimate. In the near future, we are going to have the upgrade of LHC to the high-lume LHC. This is already settled down. Here you see what would be the peak luminosity of the high-lume LHC compared with the LHC as it's running for entry. We kind of almost double it, a bit more than double. And to cope with it, we worked a lot in upgrading the CMS detector to cope with this hyperlap radiation damage. In special, the tracker is going to be way more granular. The AGCAL is going to have a very good reconstruction of the jet energy. And in special, there is the introduction of this new MPI timing detector that is a dedicated precision detector for timing of minimum ionizing particles. This means that you can time what happens with jets, big jets, and leptons better. So this is instrumental maintaining the CMS resolution and reconstruction efficiency to all the events observables. Three main key things that are going to happen with the implementation of this MTD detector is the rejection of tracks from PILAP by adding these timing requirements in the track time. Since we have this information, we are going to have this information. We could employ PILAP rejection algorithm already an online measurement. Is already embedded in the detector settings. Right now we have only offline. And then we also have removal of spurious secondary vertices, also because of this timing information. So this brings of estimation of Higgs path high-lume LHC, and to the idea that to do this projection, we can do luminosity scale of the present measurements, only with a factor kappa that says how much the luminosity is increased, but we consider the efficiency of physics subsets, reconstructions, mis-ID, and resolutions out to be the same of run 2. This again because of the MTD. For the projections, we used the main channels plus BBWW and multi-lepton. And what we can see here is the significance of the gluon fusion production with the luminosity. We say in particle physics that we see evidence when you have 3 sigma. In this purple line, you have the statistical only scenario, so it's only the statistical with the luminosity increased. But then you have the S2 scenario, that is what I described here, just assuming all the uncertainties as the standard model 1, you expect to have a 3 sigma evidence by 2000 inverse Ventoban to Autobahn. And here is what we expect in the kappa lambda, again in the standard model scenario. And then we start at the end of the high lumi to have less than 1 precision in the kappa lambda. That is a lower bound in what we expect to have in the future. Though we still expect a significant improvement in this picture that are less obvious to compute for first principles. But we are already improved at run 3 the objective identification algorithms, the trigger strategies, and analysis techniques to see that this picture, the future for the Higgs, it's much improved beyond the scope of scale of luminosity. So these arrive to my conclusions. Sorry. I hope I made the case that the measure of the Higgs potential, it's one of the key topics in high energy physics. That in LHC, it's in colliders, it's achieved directly by the search of the Higgs pairs that also allow access to another rare quartic couplings. We have a brand new legacy combination with all the channels and theory updates that we could have. We also consider the correlation of the constraints of the Higgs potential with all the other couplings that comes from the single Higgs and project this legacy HH combination for the upcoming LHC. In a pessimistic scenario, we shall have Higgs pairs by 2040 and evidence of the process. But I have faith that it is going to come much before. Yeah, thank you for the attention.
Thank you very much. I think the room is. Thank you very much. Thank you very much. Thank you very much. No, I mean outside hears us well. Now it's a bit better. Yeah. Outside hears us well. Just inside not. Okay. Finally, we found the knob. But I checked with the video service and they said we couldn't increase it. So thank you for the seminar and for sustaining despite your voice a bit failing. So the floor is open for questions. We start with the room. In Zoom, please raise your hand. Split second.
Hey, Xander, thanks for the nice talk. I have kind of a technical question. I was wondering if you guys included the fix to the Powhag simulation for this combination.
In the cross-section, but not in the simulation itself. What we did was to assure that this Powhag bug would not influence match the BB gamma gamma and the main channels, and therefore we added the effect only in the cross sections.
Okay, so the same thing that we did.
Mhm.
And when is the pass going to be public? I'd like to read it. Thanks for the nice talk, Sander. I have a kind of mean question as well. Your BB gamma gamma and BB tau tau results degraded slightly compared to in the expected limits compared to your previous results. Could you comment on what changed in the analysis or the interpretation?
Not in the analysis. What changed is what Katerina asked. What is this? The cross section itself. In the standard model, it went a bit up.
But the Powhug bug didn't affect the standard model cross section. It only affected like samples.
We also included,
You did update to the new cross section recommendation.
Fabio.
Just leave them. Wait, no, because we have 130 people outside.
It's also the uncertainty on the heavy flavor single X
Yeah.
that was added for this combination.
Because of the works of the Atlas and CMS combinations that we are doing, we added these heavy flavor systematics of 50% in the single Higgs, and those channels and single Higgs is important. I forgot. Sorry.
Can we take a question from outside, from Fabio Ceruti?
Yeah, can you hear me?
Hello.
Fabio, please.
Yeah. Can you hear me? Yes. Thanks a lot. Very interesting seminar. I have just a minor question on slide 20, where you show the limits on K lambda. Yeah. So I'm not sure, but I guess the figures are just the limits is really derived from the figure when the red curve crosses the cross-section limits, or you use the scan with the test statistics on K lambda?
We have in the past the bounds with both methods because we mostly show this one because it's what the theory side likes to look. But the limits that we derive by the upper limit are considering the theory uncertainty. And then we also have in the past the constraints considering the data statistics.
Okay, so this minus 1.4644 is not from this plot, because as you corrected pointed out, you cannot neglect the theory uncertainty because they are quite large. Okay, thanks.
I have also one question. Hello, can you hear me?
Yes?
Yes, go ahead.
May I ask what basic cuts were applied when generating events for the study of the 4B final state?
If you're asking if we have we had fiducial cuts in the simulation of the signal in the 4Bs, is that what I understand?
Yes.
We don't
4B.
have fiducial cuts. No. We don't have fiducial cuts.
Okay.
And the next question is by Alexander Belyaev. Outside. You're muted. Okay, more questions from here?
I have a question. My question.
But please raise your hand if you have a question.
Okay, understood.
Now it's the turn of Alexander Belyaev. And if he doesn't speak up, there was a question here, no? Yes.
Okay, I'll go again. This is also a slightly technical question. So your WW gamma gamma and tau tau gamma gamma analyses, how much overlap is there between these selections? Because what we saw in Atlas is that there's a huge amount of overlap with these. Can you really distinguish between these final states effectively?
We made sure, of course, to remove the overlap, but this is not something I have on top of my head. The overlap is removed for the combination itself.
Sure, but in the actual analyses, like, is the overlap large?
I don't have this information in my head. No. Sorry. Okay.
So then, Fabian, you want to ask your question? Your hand is not raised.
My question, if you can see, which amount of data has been used for this study, please?
This is Furan 2, so it's 138 inverse phantom band. This is the question.
Yes, which amount of data? 10 millions, 1 millions of data, or how much? How many, please?
I wouldn't. Yeah, this is not a number that we use much in the high energy physics results, so we don't have so much in the head. I don't know.
I mean, you can multiply it by 80 millibarn, and then you get the number of sampled events if you want. But that's of course not the recorded ones. Okay, then we have a question by William Murray.
Hello. Yeah. Well, actually, I was wanting to tell you that Sasha would like to speak, but you keep muting him. So maybe we could read his question.
I did not mute him. So, Sasha.
Alexander Nikitenko.
But we did not mute him, so I don't know. He can ask his question. Yes.
But he can't. He cannot unmute.
It doesn't work. But I think.
Okay, I'm so. Okay, let me see. I'm sorry that he cannot unmute, but I cannot help. He could write it, and then we can read it here.
But perhaps I could ask one question while I'm here. On page 17, you were showing the results for the BBVV fully hadronic, which you said is the second best channel for anomalous VBF production. But I don't think it was used in the kappa 2C limits that you gave a few pages later. Could you maybe just tell us how powerful this is?
It's here. It's just that 4B is too powerful. But this BBWW, it contains the electronic and the hadronic channel. So
okay, and it happens to make the limits slightly worse because the shape of the likelihood is such. Okay, so it's really not particularly. I mean, it's there. It's powerful. It's the second most powerful, but it really doesn't matter.
For B, it's a killer one.
Thanks a lot for the nice talk. So I had a question on the 4B results we were just on. So previously, I think the combined limit that was being quoted was a little bit stronger than the one, I think it's like 4.3 now for the expected combined limit between these two. Is that related to the theory uncertainties and things like that, or what else changed to lead to that?
The same kind of update that we did in all the channels.
Okay, that's it. There was, I'd heard from many other people is that there was also things like overlap between the two, the boosted and the resolved, that changed a little bit.
From the publication, the overlap removal didn't change. We always have the.
Okay, so that was always, you say done. Okay, interesting. So we'll have to figure that out. Okay, thank you.
Also, I think in the 4B results, when it's standard model, the VHH analysis is included.
And that we don't split, we don't show the split, yeah.
Okay, so Sasha asks for slide 22. About C2 coupling, did you use contact inclination for simulation for the gluon-gluon HH vertex?
So this is a bit of a history, because most of the analysis was done prior to the Heft simulation. So what we have is that we have the full simulation, actually the other for the kappa t and kappa lambda, and for everything that I consider C2, we use the updated Monte Carlo to do a reweighting and achieve the contact interaction in the same simulation level.
Further questions in the room or online? I don't see any, so thank you very much again, Alexandra.